let us go to the second reason which is responsible for making a vacuum tube unavailable to be used at the microwave frequency is transit angle effect. Now I hope you understand by the word transit. What do you mean by transit? Transit is something associated with movement. Okay. Now what is this transit time? So transit time means time taken to travel. From where to where? It is given by time, you all know that velocity is equal to distance by time. So time is equal to distance by velocity. So which is this distance? This distance is nothing but the separation between the cathode and the grid. Okay. So you have a vacuum tube here. So this is your cathode. So this is the grid. So the distance between these two is called as the small d. Small d is the distance between these two electrodes. Okay. And what is V naught? V naught is the velocity with which the electrons are leaving the cathode and reaching the plate through the grid. So the grid is doing the job of controlling the movement of electrons from the cathode to the plate with the control on the grid. That means you apply the input between the grid and the cathode. Okay. So depending upon this voltage, the number of electrons that are going to reach the plate is decided. Okay. So what does this V naught depend upon? So there is a small derivation on that. You can do a little bit of search, literature survey, and find out that the velocity with which the electrons are traveling is equal to 0.593 into 10 raised to the power 6 with under the root V naught. What is this V naught? V naught is the DC voltage. Why are you applying DC voltage? It is pretty much obvious that your cathode has to be negative with respect to the plate if electrons have to travel from the cathode to the anode. Isn't it that so? So you have this equation. I have taken down this equation multiplied by omega on both the sides. Now why we need to multiply by omega on both the sides? We are talking of about the behavior of a vacuum tube at high frequency, and omega is a quantity which, if included into the expression, will give us an analysis of how this happens at high frequencies. Okay. So we all know what is omega into T, isn't it? You know omega equal to theta by T. So omega into T is equal to theta. So if this is theta g is equal to omega d divided by V naught. I hope you are clear with what is omega, what is small d, and what is small v naught. Please note, small v naught is velocity and capital V naught is your DC voltage. Okay. Now let us see why should we consider about this. Now let us go back to understand what happens. Okay. So there is a non-zero amount of time. See, when your cathode is made negative with respect to your plate, what happens? So this is called thermionic emission. I think you know about a vacuum tube. So when current is passing through this material, it gets heated up. Because it gets heated up, what happens? Electrons are emitted out of the surface of the material. So electrons are emitted by the cathode. So where they have to go? They have to be going to the plate. Why to the plate? Because plate is positive with respect to the cathode. So students, what we have to understand here is the electrons take a non-zero time, a fixed amount of time to leave the cathode and reach the plate. Okay. So this is the transit time that we are talking of about. Now this transit time is not to be considered at low frequencies. Now why? Say at low frequencies, when frequencies are low. So at low frequencies you are having that frequency is inversely proportional to time. So low frequencies will have a large time period and high frequencies will have a small time period. You know that, isn't it? So now at the grid, if you are applying a sine wave like this at microwave frequencies, what will happen? That means these frequencies are very high, that means the time period is very small. So this effect called as transit angle effect becomes very, very important at microwave frequencies, because what if this voltage changes even before the cathode, even before the electrons leave the cathode and reach the plate? By the time they have come here, this would have become negative. So you know, no, because the time period is too small, they are quickly changing in a small interval of time. So what happens is the electrons are not given time to reach the plate as a response. At low frequencies, the voltage is changing slowly, so the electrons are also able to respond to these changes in voltage. But if this signal is varying at a very high frequency, even before the electrons respond, the voltage has changed. So what is the effect? The effect is that the electrons will never reach the plate and they will keep oscillating between the grid and the cathode. So what does this happen? This is going to apply a limitation on the operating efficiency of the vacuum tube. What do we want the vacuum tube to do? The vacuum tube should respond to the input voltage. So when it is not able to respond, why it is not able to respond? Because there is a non-zero value of transit time, and that time is very large when compared to the time period of the applied signal. So this transit angle effect becomes very critical when the applied signal's time period is comparable with the time period or the time taken by the electron to leave the cathode and reach the anode. So this is an important limitation, meaning to say at high frequencies, because of the transit time, the vacuum tube is not able to respond to the to work the way it has to at high frequencies. So let us discuss on the last limitation of vacuum tubes, that is the gain bandwidth product limitation. So what about this? See, gain into bandwidth is found to be a constant. So if you look into the textbook, it zeroes down to something called as GM divided by C. GM is also a constant and C is also a constant. So this is independent of frequency. So gain into bandwidth is equal to constant. So why is this a limitation? Let us try to analyze. Now see students, again thinking of what we have learned with the ideal characteristics of an amplifier. What do we want in an amplifier? An amplifier should have infinite gain and infinite bandwidth. Suppose if you want, in this case, if you want the gain to be very large, okay, you want a large gain. But then this is a constant, this product will always be a constant. So what should happen to bandwidth? The bandwidth has to reduce to compensate for this increase so that this product will remain a constant. I hope you understand. Now if you want a large bandwidth, if you want an amplifier which is going to have a large bandwidth, then what should happen? Then the gain has to fall so that this gain into bandwidth product will remain a constant. So what do we infer from this? So given a vacuum tube, you cannot have best of both the worlds. That means you cannot have a high gain and a high bandwidth with the same vacuum tube. I hope you understand. So this is another limitation of a vacuum tube which makes it inoperable, or it cannot be used at microwave frequencies. So this happens to what kind of devices? This is a limitation with resonant circuits. Now why did I tell resonant? I asked you to remember, I told you what is a resonant circuit, the ones which is having L and C. So you've seen that in the equivalent circuit of the vacuum tube you have both L and C. So definitely it is a resonant circuit. So what will happen? This is definitely going to be a limitation of the vacuum tube which makes it inefficient at microwave frequencies. So how to overcome this limitation? This limitation can be overcome if, because it is resonant, this is a problem. So what is the solution? It should be non-resonant. So there are few structures called as slow wave structures which are non-resonant, and that's how this gain into bandwidth product being a constant limitation can also be overcome.